Hi, so welcome to the lecture on measures of spread. So previously we've talked about distributions of data, where we've talked about what are the possible values in a data set and how frequently they occur. And then most recently we talked about the center of a distribution. Well, now in this lesson we're going to look at measures of spread for a distribution. So how spread out is the data? Is it all clumped together in the middle, or is it really spread out? We're going to look mainly at two measures of spread: the range and the standard deviation. Some other ones will come up a little bit too, but those are the main two. And then we're also going to look at outliers. So let's start with the range. The range is just the maximum data point minus the minimum data point. It's not incorrect to say that the data ranges from the minimum to the maximum, but when you're asked to give the range, they're asking for the maximum minus the minimum data point. So in this data set, we've got the smallest data point is 20. The highest data point, not the tallest, the highest data point is 100. So 100 minus 20 is 80. In this second data set, our range turned out to be 6. So in that sense, we would say that the first data set is more spread out than the second data set. The hard thing about range is that it is extremely affected by outliers. So if we have just one of those data points that changes, say we changed, 73 to 7, then our range is going to change by a tremendous amount. So for that reason, the range isn't that useful of a measure of spread. The one we really use is the standard deviation. And if you take the standard deviation, if you take the term standard deviation and break it up, it kind of gives you an idea of what standard deviation is. So if you look at standard means typical. I shy away from using the word normal, but because in stats class normal means something different. But typical and deviation means distance. So the standard deviation is a measure of how far away a typical observation would be from the mean. It's not quite the mean of the distances from the mean, but if you're thinking about it that way, you'll be on the right track. So we've got a sample standard deviation and a population standard deviation, a statistic and a parameter. The statistic is the sample standard deviation, and the notation for that is S. The notation for the population standard deviation is sigma. And so we would use S, which is a statistic, to estimate the parameter sigma. This is just like with the previous notation we've seen. It's very important that you learn this notation. I will ask you about it over and over again. And just like before, with the other ones I said previously, there will be problems later on in the semester where you're going to have to read a problem and where they say the sample standard deviation, you're going to need to know to plug that in for S. So you really need to know this notation. All right, so far we've got X bar, mu, N, S, and sigma. Okay, so 5 pieces of notation that you need to memorize. You'll see that the notation SD in academic journals for the standard deviation, and usually they mean the sample standard deviation for that, but that's not notation we're going to use in this class. All right, so here's the formula. And And let's look at what this formula does. So the top part of this formula is where we start. So x means every data point, and then x bar is the sample mean. So we take every data point minus the sample mean, square the results, then take the sum of all of those, and then we divide by the sample size minus 1, and then we take the square root. If you didn't catch all that, no worries. We're going to do some examples. So if this is our data set, we're going to start with a table of just each data point. And then we're going to take each data point minus the mean squared. So we first have to actually calculate the mean, which turns out to be 70. So if we subtract 70, because it's the mean, from each one of these data points, square the results, we do 67 minus 70, square that result, and we get 9. 68 minus 70, square that result, and get 4, etc. So the top part is we've done this much, and now we need to take the sum. So when we take the sum, so we just add up all of these, and we get 26. So we've done now the top part of this formula. So we've done, that's this much. So now we just need to divide by n minus 1, and then take the square root. So we've got 5 observations in the data set, so that's just n equals 5. So we're going to subtract 1 from that, which we get 4. So we take the 26 we calculated, divide it by 4, and then take the square root. And we get a sample standard deviation of 2.5495. Okay? So again, just to recap, we took every data point, we subtracted the mean, we squared the results, we added those up, and then we divided by the sample size minus 1, don't forget the minus 1, and then took the square root. Your textbook talks about a shortcut formula for standard deviation, but I don't want you to use that. I'm going to insist that you use this formula because, for one thing, it's not really shorter, but also the shortcut formula doesn't help you understand what's going on. For me, when I first learned this material, once I did this a few times, I kind of realized what standard deviation was telling me. And let me go back just a little bit and tell you sort of how it works. If you think about it, and for just a minute here, it almost pains me to say this, but for just a minute here, we're going to suspend order of operations. And so we're going to talk about sort of what this formula almost sort of does. So every time we take x minus the mean, that gives us a distance. Okay? Now we square it, which makes it positive, and then we take the square root. So if you imagine, these almost sort of cancel each other out. So we're kind of taking a bunch of distances. And now taking the sum of them and dividing by almost how many they are, it's just almost the mean of the distances, even though we had to fudge a little bit. But basically that's what's going on here. So this is almost like the mean of the distance between the distances of the x's and the sample mean. And I think if you do it by hand a few times, it'll at least maybe start to sink in. So anyway, so I'm going to ask you to do the standard deviation by hand on homework and on the test. But unless it specifies doing it by hand, then you can just do it in StatCrunch using the descriptive statistics. And by the way, when I say by hand, I mean, you can use the calculator for squaring, for taking the square root, for adding, subtracting, multiplying, dividing, and square roots. It just means do it using the formula, not using a built-in something in StatCrunch or SPSS. So back to the same two data sets that we were looking at earlier. So we had data set 1 and 2. The standard deviation for the first data set we calculate to be 30.6186, and for the second one it's 2.5495. And I'll show you how to use StatCrunch in just a minute for getting that. But since the first data set has a larger standard deviation, we would say that it has a larger spread than data set 2. Though it is kind of hard to compare standard deviations directly to each other like that. Let's talk about variance just a little bit. The standard deviation squared is itself a thing. It's called the variance. For statisticians, it's useful to look at because it has properties relevant to the normal distribution. But for us, it doesn't really matter. If in my stat lab or something you encounter a question where they ask for the variance, you can just take the standard deviation and square it. Or you can just get the number before you take the square root in the standard deviation calculation. The standard deviation that we calculated was for the sample. And that's going to be what I ask for. There is a slightly different formula for the population standard deviation. The only difference really is instead of dividing by the number of observations minus 1, you divide by the number of observations. But don't worry about that. We're not going to cover it in this class. It's not all that useful for us. Okay, now let's talk about box plots. So we've looked at box plots before, but now let's look at them in a little more detail. So this was a data set I made up to be waiting times at a doctor's office. So this is the data, and this was the box plot. And first of all, let me show you how I generated that box plot. So I'm going to select the data, and I'm going to go over to StatCrunch, and there's the data. So just copy and paste the data, and I'm going to it's under graph. So it's under graph, box plot. I'm going to select our variable, and down here where it says use fences to identify outliers, make sure that box is checked. Okay. One really nice feature about box plots is that they will show you outliers. So if you hit compute, that gives us our box plot. Now, with the graphs, in StatCrunch, they're a little bit harder to copy and paste over. So if you see here, I picked options copy, but then it gives you the instructions down here. Right-click the image and do, I forget every time how to do this. Copy image, and then Control-Alt-V. So if we go over to a Word document, we would do Control-Alt-V and paste it as device-independent bitmap. All right, but just like before, you can always do a screenshot if you have trouble with that. All right, so back to our box plot. So here's what this box plot tells us. We start with the box in the middle. The line in the middle of the box is the median. The two lines that make up the box are the 25th percentile and the 75th percentile. In other words, the value of the data where 25% of the data is below it, and then where 75% of the data is below it. So this box represents the middle 50% of the data. So that's the box. Then there's an outlier. The outlier is determined by a formula, which we're not going to get into. We could. You're perfectly capable of doing it. It's just not something I want to spend time on. So this tells you that according to a certain definition of what constitutes an outlier, this data point is an outlier. So there is a data point, there's a point in the data set, 1, that's an outlier. The whiskers go out to the highest and lowest observations other than outliers. So other than the outlier of 1, these are the highest and lowest observations. All right? Where box plots are really useful, two things. One is in determining outliers without you having to actually do any calculations. And the other is if you're comparing two data sets, which we're going to do next week. So again, from looking at the box plot, we see the middle 50% of the data is between 8.36 and 5.55. We can see that there's an outlier at 1, and we can see that other than that outlier, the lowest data point is 3.82, the highest data point is 10.49. Here's a box plot of that same data from SPSS, and I'll show you how to do that. Let me point out, though, there's one different thing in SPSS, and that's this number here. This number represents the case number, meaning that's the 12th row of data in your data set. That doesn't mean that there's a data point that is 12. That doesn't mean that this represents a waiting time of 12 anything. It just means that's the 12th row of data. So that's a mistake that people often make. All right, so let's go back over to SPSS. And this is exactly the same thing you did before. Analyze descriptive statistics. Explore. We're going to take our variable, move it over. And now we do want plots. So we'll just click both. But we really, right now, we're not looking at the stem and leaf or the histogram. So we'll click OK. And by the way, this gives you some of the other things that we talked about. This gives you the range of this data. It gives you the variance, although we don't really need it. It gives us the standard deviation, that's the sample standard deviation, and the range. And then here's that box plot. And I think I've done this before, but just to reiterate, to copy this over to Word, you can right-click and copy as EMF, and then go over here to a Word document, and I just do Control-Alt-V and paste it as in, that must be what EMF stands for, Enhanced Metafile. Click OK. and that'll give it to us. There was one more thing I meant to show you from StatCrunch, and that's how to calculate some of the other things you want. We did this before basically, but bear with me. So if we want the standard deviation and the range from StatCrunch, we'll go exactly the same place we did before to get the mean median. So we're going to Stat, Summary, Stats, Columns, and we'll select our variable. And actually everything we want is selected here already. So if that's the case, you don't really actually have to do anything else, but you probably well, maybe want to select just what you need. And there's one more thing I wanted to mention here. The standard error, that is different from the standard deviation. So don't get that confused. Standard error is something completely different. So let's pick the mean, and I'm holding down the control button as I do this. The standard deviation, the median, the range, and then a lot of times it's nice to know what the min and max are. The min and max are actually kind of measures of spread. And I guess we'll call that good. So when we hit compute, this gives us everything we need. All right. So that's it for this lesson. And as always, let me know if you have any questions.